welcome to The Explainer. So, today we are going on a bit of a journey to uncover the hidden reality of deploying artificial intelligence. And we're not talking about pristine, climate-controlled data centers here. We're talking about out in the wild on real-world industrial hardware. We're looking at this really fascinating piece of research from Vahid Faryad called the LongHaul-Bench. And it asks a question that could honestly determine the entire future of automated manufacturing. I mean, think about that for a second. We pretty much all assume that when an AI agent learns from experience, it obviously gets smarter, right? But what if it doesn't? What if over thousands of tasks, it actually starts to silently rot from the inside out? Do these self-improving agents truly get better, or are they just compounding their own mistakes until they literally lose their minds? Okay, let's dive into this roadmap really quick. 1. The industrial edge problem. 2. Enter the long-haul benchmark. 3. Does AI memory rot? 4. The double-edged sword. And finally, 5. Real hardware realities. So, Section 1, the industrial edge problem, where AI meets reality. You know, most of what we hear about AI is all about the cloud. You've got these massive trillion-parameter models with virtually unlimited compute, solving isolated single-episode tasks like writing a Python script or summarizing an email. But edge AI, specifically industrial edge AI, it's a completely different beast. These models are offline. They're squeezed onto highly constrained hardware. And most importantly, they run for months on end, accumulating thousands of experiences across sequential diagnostic episodes. It's a gritty, resource-starved environment. And here is exactly why this matters: the sheer stakes involved. If a cloud AI gets a trivia question wrong, whatever, you just refresh the page. But if an industrial diagnostic agent gets confused on a factory floor because its knowledge base is corrupted, it could start giving confidently wrong maintenance advice. We're talking about massive physical machinery here, huge financial damage, and honestly, major safety risks. All right, Section 2. Enter the long-haul benchmark, the ultimate marathon. So, Faryad's research is essentially setting up the ultimate marathon for AI. Let's walk through this timeline. At Episode 1, our diagnostic agent boots up, totally fresh and clean. By Episode 100, its memory is actively shaping its decisions based on past maintenance logs and alarms. But by Episode 1000, we really have to ask, what is the actual state of this agent's mind? Because the danger is that the system can stay totally online, functioning perfectly on the outside, while its internal knowledge is just slowly degrading, and errors are compounding silently. To understand how this degradation happens, we have to look at how these agents actually remember things. The benchmark tests a couple different improvement operators. First up, we have append-only memory. This is exactly what it sounds like. The AI just naively stores a summary of every single episode. It's basically digital hoarding. Then we have gated memory. Now, this is much smarter. It uses error-driven writes, meaning the agent only records a new memory if its current knowledge failed to predict the right outcome. So it actually tries to learn from its mistakes rather than just accumulating useless noise. Which brings us to Section 3. Does AI memory rot? Let's get into the experiment results. Now, we need to talk about the massive gap between what is happening and what's actually possible here. The frozen control, which is an agent that learns absolutely nothing at all, scored 58.2% accuracy. The append memory agent, the one that just hoards all its experiences, bumped that up to 62%. So memory helps a little bit, right? It adds about 3.8 points. But look at the manual Oracle benchmark. If you manually feed the agent the perfect, exact correct row every single time, it hit 76.8%. That tells us current memory systems are leaving massive, massive headroom completely unused. But honestly, it gets a bit darker. What happens when the AI starts learning the wrong things? The researchers introduced this concept of plausible poison, which is basically a wrong but totally believable diagnosis being confirmed as correct in the AI's feedback loop. It's kind of like compounding bad habits. With zero corruption, the agent sits around 59.5%. At a 20% corruption rate, accuracy drops to 55.8%. But at a 40% rate of plausible bad feedback, the agent plummets to 53.6%. And here is the crazy part. That is actually below the no-learning frozen control. The agent literally performs worse than if it had never learned a single thing. Moving on to Section 4, the double-edged sword, the impact of recall. If there is one thing you take away from this explainer today, let it be this: plausible wrong recall hurts twice as much as correct recall helps. Memory is a double-edged sword, for sure, but the blade facing the AI is quite literally twice as sharp. And this brilliantly illustrates exactly what that double-edged sword does to the data. By pairing the exact same episodes, the researchers isolated the pure effect of the memory. When the agent recalls a correct past experience, it boosts accuracy by 9.4 points. Awesome. But when it recalls a misleading memory, it completely derails the agent, just destroying accuracy by 19.7 points. The memory mechanism acts as an amplifier, and wrong memories are massively destructive. Recall precision is the absolute binding lever here. Finally, Section 5, Real Hardware Realities, Deploying to the Edge. So, big question. Can a modern AI brain actually fit inside a constrained industrial device? Well, surprisingly, yes. The researchers measured a strict 8 GB RAM limit. The quantized Qwen 3 billion parameter model takes up 3,650 megabytes. The embeddings take 174, the Python agent stack takes around 128. Add all that up, and you have a fully functional on-device AI running in about 4 gigabytes. That leaves roughly another 4 gigabytes of free headroom on a standard 8 gig class device. It's totally doable. Take this STM32 board, for example. It's a highly constrained 4 gigabyte compact target. For a tiny board like this, you'd likely need to step down to something like a 1.5 billion parameter model, but again, it is entirely within the realm of physical possibility. And, if you step up just slightly to an industrial board, like this 16 gigabyte NXP unit, fitting that full 3 billion parameter model becomes entirely plausible. The compute itself is no longer a theoretical barrier for industrial facilities. But of course, theory and practice, they often clash, right? Going from the beautiful theoretical flow of industrial data over to a physical target platform like the Qualcomm RB3 Gen 2, it's not seamless. While the RAM math works out perfectly, the researchers noted that getting the software to actually play nice with edge toolchains, dealing with NPU delegates and Int64 truncation, that remains a major engineering hurdle. Profilers can tell us, yeah, it runs, but it takes immense work to ensure it runs reliably. And look, there is one final physical limit we just can't ignore: the context budget. Your hardware literally forces you to forget. In the 1,000 episode test, the basic append memory model was forced to evict 895 out of its 995 experiences. You simply cannot remember everything when you live on the edge. You have to be absolutely ruthless about what you keep, because as we learned earlier, keeping the wrong thing will completely destroy your accuracy. So the crucial point is this. First, as we deploy AI out to the industrial edge, we're dealing with systems that are incredibly long-lived and highly constrained. Second, we know that current memory systems are leaving massive headroom on the table. Third, we know for fact that bad recall degrades performance twice as fast as good recall improves it. And finally, we know that these highly capable 3 billion parameter models can functionally fit inside standard 8 gigabyte industrial hardware today.
The hardware is ready. The models are shrinking. But that psychological challenge for the AI, that remains. As AI moves from the pristine environment of the cloud to the gritty, unpredictable reality of the factory floor, how will we build memory systems robust enough to prevent our smartest machines from slowly losing their minds? That's the real challenge ahead of us. Thanks so much for joining me on this explainer, and keep questioning the data.